Hey everyone, this is Doug. I'm going to go over some airfoil analysis here. What I've got is some data that I pulled off of airfoiltools.com for the NACA 2412. In fact, I'll put that on here. The NACA 2412 airfoil at a Reynolds number of 1 million and an N crit of 9, I believe, is what I got this from. N crit basically is a turbulence level in the simulated wind tunnel when you're running X-foil. It has to do with instabilities in the flow that are associated with turbulence. So N crit of 9 is a pretty clean wind tunnel, meaning that you have pretty low turbulence. As far as I understand, I haven't looked at this for a while. I believe the lower numbers of N crit mean more turbulence. But anyway, the N crit of 9 is kind of a standard that most people use as a starting point for low turbulence flight. Just normal free stream flight. So anyway, I went on and they have this data a lot more. They have this at every, I don't know, half a degree or something like that, or every 1 degree. And I've just pulled off here in increments of 2 degrees. And so let me just plot some of this stuff and we'll talk through it and talk about how we fit this now to equations then that would represent this data. So I'm going to insert a chart, and the default here, I'm using Google Sheets. You can be doing this in Excel or really any spreadsheet program, but the default here is for it to come up as a column chart. So you have to switch that to a scatter plot. So now you can see the data there. On the x-axis we have angle of attack in degrees. Y-axis we have the lift coefficient. You can see that that's pretty linear. What I like to do then is to fit an equation through this. So rather than store all of this data, which you can do, if you're running a big simulation or designing an aircraft, you can store all of this data in a lookup table when it's needed, as a function of angle of attack. Usually we're looking up things as a function of angle of attack. We want to know what the lift is, and then we look up the drag as a function of lift, and we'll talk about that in a second. But I like to fit equations to this so that I don't have to use a lookup table, and the equations are usually fairly accurate. So let's go over here to customize, and we'll click on this data set here. We've got some options here. I'm going to click on trend line, and yes, we want a linear trend line. You can see it drops a line in there through the data, and that fits the data really quite well. Certainly within the accuracy that this data is good. So we don't know the lift coefficient any more accurate probably than this trend line is representing it. And then if you come down here to label, you can say use equation, and it will actually give you the equation. So this is the equation of y as a function of x, where x is the x-axis down here. So this is really the lift coefficient as a function of angle of attack. Now, so we can see that this is just a line. So we've got a slope of 0.109 times angle of attack plus 0.231. So 0.231 is the location here where we're crossing the y-axis. Anyway, so we're going to talk about, though, more useful forms of this equation here. Usually, so some people will plot lift as a function of angle of attack in degrees. I actually prefer it in radians. And one of the reasons for that, so what I'm going to do here is I'm going to say this is the angle of attack in radians, and you can just say equals radians of this number over here, and it will take that, it will assume that that's in degrees and compute it to change it to radians. We'll autofill that. So now we have a column that's radians instead of degrees. And so I'm actually going to redo this plot here, lift coefficient as a function of radians. So let's insert a chart. And again, we've got to change that to a scatter. We'll fit a line through that. So here's our trend line, and we'll put the equation on there. Okay, the reason I like this in radians, and some software packages actually require that you do this in radians, and that's because of this slope right here. So from thin airfoil theory, this is a theory out there that I have some videos on. You can look it up if you're interested. But from thin airfoil theory, you can predict that the lift slope is really close to 2 pi if you're looking at it in terms of radians, okay? So pi is about 3.14. If you times that by 2, that's 6.28. So we can see that our lift slope here is just below that theoretical thin airfoil theory solution of 6.28. So that gives me a lot of confidence in this data that it's really close to what thin airfoil theory says it should be. And then again, we still have that 0.231. That's the location where it crosses the axis over here. So, so what we want to do is I'm going to write some variables down here. So usually we characterize the lift. Instead of storing all of this data here, I'm going to characterize it by just two variables. And one of those is the lift slope, which we call CL comma alpha. And that's the 6.26 in per radian. So sometimes I'll put this in here. So this is 1 over radian. And then the other thing that we need to know to characterize this is what's called the zero lift angle of attack. Now that's the angle of attack where we produce zero lift. So you can look along this line, and actually you can use this equation. You just set this equal to 0 and solve for x in this equation, and it will give you an exact number in radians. You got to remember we're in radians here, so this is an angle of attack in radians. But for our purposes here, I'm just going to kind of look at, this is about the right point. So this is at minus 0.035. So I'm going to put in minus 0.035. So that's the zero lift angle of attack. And so we call that alpha sub L0. So that's the angle of attack that produces zero lift. So with these two, with this bit of information now, we can predict the lift coefficient at any angle of attack. And so I'm going to insert a column here, and I'm going to say this is the CL prediction from that equation. And the equation then that gives us the lift coefficient says that the lift coefficient is equal to the lift slope, CL alpha, and we want that to stay constant. So I've got to put some dollar signs in front of it. So there's our lift slope times the angle of attack minus alpha L0. And again, I want that to stay in that. So basically what I'm doing here with this equation is, yes, let's autofill that. So what it's doing is it's pulling the angle of attack over here, and it's saying at this angle of attack, I want to predict what the lift coefficient is. And so I'm going to use this equation, and these are the two parameters of that equation. One of them is the lift slope as a function of angle of attack, and one of them is the location where our lift is 0, or the angle of attack where our lift is 0. So anyway, so you just put that equation in there, and then you can autofill that down. And so now at each one of these points, we have a predicted lift coefficient, and we can compare that to the actual lift coefficient. So let's do that. So we'll insert another chart here, and we want this to be scatter. So, so basically at each of these angles of attack, we've got the blue, which was the original data, and then the red is our prediction, which is just this straight line prediction basically that was fit through that data. Okay, so now in aerodynamic software, you only have to store these two parameters, and we can predict the lift coefficient at any angle of attack. Okay, so this is the way I usually like to do it. Now, of course, this does not capture stall. Once we get up to a really high angle of attack, then the wing will stall, or the airfoil will stall, and so this is only capturing this below stall linear region. And we'd have to fit a higher order polynomial or something above that stall region if we wanted to capture some kind of a stall behavior. But a lot of times the analysis that we're running on aircraft is all below stall. Above stall is just kind of this thing that we have to deal with if we ever get into it. But really, usually we're trying to get out of stall as quickly as possible and back down into this below stall region. So a lot of the design work happens here below stall. So, okay, so that's our lift coefficient. Now let's look at, I'm actually going to jump over to the drag coefficient next. And I'm going to get rid of a few of these plots that, okay, so this is my most general trend line through that lift coefficient. We'll keep that up there. Okay, so drag now, the equation for drag, we usually assume that it's parabolic with lift. And there's a few different reasons of that we won't go into right now, but rather than plotting it as a function of angle of attack, which you can do, and actually because lift is a linear relationship with angle of attack, the plot will look very similar, but usually we write it in terms of lift instead of angle of attack. So I'm going to have lift coefficient on the x-axis and drag on the y-axis this time. Insert a chart. Here's our scatter plot, and so you can see that that looks kind of parabolic as a function of lift coefficient. Now let's add a trend line through that. Okay, so we're going to use, use equation. Okay, so the trend line, when I clicked on trend line, the default is to be a linear trend line. So it's trying to fit a straight line through this data. You can see it in faint blue right here. Not a very good fit to the data. So we actually want to go to a polynomial, and it will allow us to choose the order. And second order is usually what is used for drag. So we're assuming that it's parabolic with lift here, and that does a fairly good job. And again, you know, there's quite a bit of, if we were to plot the uncertainty in this data, you know, this data is probably not good to more than 5%. You know, there's 5% uncertainty at a minimum, I would guess, in this data. So, you know, we have some vertical room here, and the curve here is basically capturing this data within that level of error. So this is a pretty decent fit. And then I put the equation up here. So that's our equation now. So the parameters now that we can use to predict drag, one of those is going to be called CD0, and then I call the other two CD1 and CD2. So CD0 is the constant that's independent of lift. If you look over here, we've got three terms here. One of those is just a number. The second one is a number multiplied by x. And so that's multiplying whatever's on the x-axis, which is our lift coefficient. And then the third one is a number multiplied by the lift coefficient squared. So this is just a parabolic or a quadratic second order equation that goes through this data. And so this first number here, CD0, is just this constant out front, which is, let's see, that's going to be 0.00614. The next one is this linear term, which is minus 0.00354. Let's see, make sure I did that right. I think that's right. And then finally, the last one is 0.00852, and that's the lift squared term. So we've got this constant, and then a linear term, and then a squared term here. So now let's use that equation to predict what the drag is going to be at any angle of attack. And again, we'll just, or at any lift coefficient, excuse me. And again, we'll just use the lift coefficients that we have over here. So the drag prediction would be equal to CD0, and we want that to, we want to keep using that cell even when we copy this down, plus whatever's here, and again, we want to keep that cell, times the lift coefficient over here, plus this term here. We want to hold on to that cell when we copy this down, times the lift coefficient squared. Okay, so okay, and then yeah, we can autofill that down. So this is our drag prediction. So let's see how that compares now if we take the lift coefficient, our true lift coefficient, and then drag and our drag prediction based off of that equation. So we want this to be a scatter. Oh, I didn't like that. It's doing, okay, we're gonna have to fix this here. So basically what we wanted was on the x-axis, we wanted the lift coefficient on the x-axis, and then we can get rid of that on the y-axis. Okay, there we go. All right, so CD is in blue. That's our original drag that we had from our data. So that's the blue. And then the red is going to be our new prediction based off of this equation here as a function of lift. So lift is on the x-axis down here. So you can see that matches up fairly well. So, okay, so that's how we come up with these three parameters. And again, the nice thing about this is that we only have to store, let me see if I can delete this. Yeah, okay. So we only have to store these three parameters. We just have to have those three numbers in our software, basically. And now we can predict the drag at any lift coefficient. And of course, this is still limited to below stall in this linear relationship between alpha and angle of attack and lift coefficient. Now, if we get above stall, our drag usually shoots up rather rapidly. And so we, again, have to have another polynomial outside of this region here, if we wanted to capture stall effects, drag at really high lift coefficients. Now, these lift coefficients are already going up to, what is this, about 1.2. So I'd expect we're at about our stall point here. We're not going to get much higher than that. Some airfoils can get up to about 1.4, 1.6. But anyway, we're pretty close to stall there. So outside of this region, we'd probably want to fit another polynomial or something out here if we needed to predict the drag above stall. Now, one thing, this was a great question from someone recently that asked, well, what about the drag bucket? Some airfoils are designed, and I wish I had an example here, but I can draw one over here real quick. So some airfoils are designed where their drag kind of comes down like this, kind of parabolic, and then they have this drag bucket that kind of looks like this, and then it goes back up. And and these are more sophisticated airfoils that are trying to capture like laminar flow effects and things like that. And so these are actually fairly common for really optimized aircraft. So one way to treat that is you can actually fit two quadratic equations through this. You can fit one quadratic equation that is used for the lower, you can basically fit this data in here to a quadratic that I've shown here in green, and then you can fit the data outside of the drag bucket to another quadratic, so something like that. And so you'd actually have two equations. So if we come back over here, we'd have three parameters that are describing the drag bucket, and then we'd have three more parameters and we'd have to come up with those coefficients that are describing the data outside of the drag bucket. And then you can use a blending function basically to say in this region we're going to use this one, and then we're going to blend over and use this information down here, this parabola, and then at some point we're going to blend back up and use this other stuff. So anyway, there's some tricks like that you can use so that you still only have to store very limited amounts of data to be able to capture that entire drag information as a function of lift. Now, drag as a function of lift is often called the drag polar. So you'll see that out in the literature, and some of these software packages will just output the drag polar, and that's drag as a function of lift. And a lot of times they flip the axes, so they'll put right here we have drag on the y-axis and lift on the x-axis, but in a drag polar traditionally they actually flip the axes and have lift on the y-axis and drag on the x-axis, and that's just kind of a convention for a way to look at it. But I personally like keeping lift on the x-axis because then I can use these auto-fit types of things that are built into a lot of these spreadsheets, for fitting parabolas. If we flip the axes, it's very difficult to have an auto-fit up here to the data because it's actually not a function anymore because you've flipped the y and x axes, and there's actually two solutions for locations along the x-axis. So anyway, that's kind of outside of the scope of the point of this video, but I just wanted to point that out. Okay, so the last thing here is our pitching moment that we haven't looked at. So let's look at pitching moment, and there are actually two different ways to look at that. Sometimes those are characterized as pitching moment as a function of angle of attack, and sometimes they're characterized as pitching moment as a function of lift coefficient. So let's just look at the different ways to look at that real quick. So let's insert our chart, and we want this to be a scatter plot again, and for some reason it's we want that to be on the x-axis. Okay, so here's our pitching moment as a function of angle of attack, and while I'm at it, I'm just going to plot pitching moment as a function of lift coefficient so we can kind of compare the two. They're actually going to look very similar because let's see. Okay, there we go. They're going to look really similar because lift and angle of attack are related linearly. And so because of that, you can see these two plots look almost identical. One of them is plotted as a function of lift coefficient, the other as a function of angle of attack. Really, all they are shifted left to right relative to each other, because here on the x-axis we have angle of attack, and here on the x-axis we have lift coefficient. So you can look at it either way. Now, a lot of times the pitching moment data is a little bit messier, and part of that, is due to the fact that a lot of people use Xfoil for their airfoil analysis, and Xfoil for some reason I think really struggles with getting accurate pitching moments, and so you can even put in like a symmetric airfoil. I hope I'm saying this correctly. It's been a while since I tried it, but if I remember right, you can put in a symmetric airfoil and run it as a function of angle of attack, and the pitching moment sometimes isn't even symmetric, left to right, which you would expect, or there might be some big discontinuity here in the center. And anyway, I just haven't had a lot of luck with pitching moments, so especially coming out of Xfoil, so I don't really trust it a whole lot. So this data, it's a bit erratic, but we're gonna fit it to a line anyway. So let's add a trend line and say yes, we want a linear trend line, and let's show the equation up here. So this is the pitching moment as a function of angle of attack. So the way that we would characterize this, and you can see how well it goes through the data. I mean, the data is pretty nasty. And sure, you could put a higher order polynomial in here, but in my opinion, you're capturing noise. You're not capturing real aerodynamics of this airfoil. So, I think the error bars in this are pretty significant. So, one other thing to note is that the pitching moment at the quarter chord of an airfoil, which is where Xfoil is reporting this data, is at the quarter chord. The pitching moment doesn't change significantly as a function of angle of attack, and that's part of the problem. That's part of the reason we see so much variation here, is because there's actually very little change as a function of angle of attack when you're measuring the pitching moment at the quarter chord. Now, if we were measuring it at the leading edge, or at the trailing edge, or at the 3/4 chord, or even at the half chord, we would see this pitching moment vary significantly. But anyway, at the quarter chord, it doesn't vary a whole lot. But in theory, it should be somewhere close to a linear relationship with angle of attack or with lift coefficient. So that's what we're going to use here. So we're going to say, we're going to capture this by saying we've got a Cm comma alpha. And by the way, whenever I use a comma, that means a derivative with respect to. So this is the change in pitching moment with respect to alpha, which is going to be the slope of this line, which we can see right here is 0.0235. Okay. And then we could also characterize this. We need not only a slope but then an intercept, and we can usually the intercept then that we would use here is Cm at alpha naught, which is, or you can call this Cm0. This is the pitching moment at 0 angle of attack. Okay. So that would be this value here. Now it's going to be, actually it's when x is equal to 0 here, when we put in a 0 for the angle of attack. So from this equation it would be minus 0.0502. Okay, so that's our prediction for the pitching moment at 0 degrees angle of attack, and it's actually where this line crosses, not where the data is. It's what this line is predicting. So another way to look at pitching moment is as a function of lift coefficient. And so here we could say this is the change in pitching moment with respect to CL instead. So let's put a trend line through this. Let's see. Okay, so we're going to add a trend line, and we want it to be linear, and add the equation up here. So the change in pitching moment with respect to lift coefficient here is 0.00343, and then we'd have Cm at 0 lift. Okay, so the pitching moment when lift is equal to 0 instead of a equals 0. I'll put it on a little a here. This means that the pitching moment when the angle of attack is 0 is this. The pitching moment when the lift is 0 is where this line, our prediction for it at least, is where this line crosses the y-axis. This is the point of 0 lift, because remember we have lift on the x-axis here. So the point where this line is going to cross is our pitching moment at 0 lift, or at least our predicted value of that, which is just this value right here. When we plug in 0 for x, we get minus 0.051. Okay, so these are two different ways. These are going to give us the same solution. Basically, you know, we can use this equation here, or we can use the equation based off of this information to give us the predicted pitching moment as a function of angle of attack or lift coefficient. So let's just do one of those as an example here. So let's say this is my CM prediction, and it's going to be equal to, let's use this angle of attack for now. So CM alpha, and I want to keep that guy in that, looking at that cell, times our angle of attack. And remember, I did this in terms of radians. Again, it's nice to either stick to radians or degrees consistently. I stick to radians consistently for all of my computations. So that's the times the angle of attack there, and then we need to add the CM alpha is 0, and let's see, let's put the $sign on there. Okay, so this is our prediction. We'll autofill down, and so now let's check out as a function of angle of attack, what's the difference between CM and our CM prediction. So we'll insert a chart. And we want this again to be a scatter, and the x-axis we want angle of attack. And okay, so there we go. So there's the blue again is the actual data, and it looks identical to this plot here, right? And then the red should basically represent this line that goes through it. We've computed the pitching moment at any angle of attack in here, and we can plug in any angle of attack. You know, the point of these equations here is that we can now plug in any angle of attack, whether or not we have data there. We can plug in a point, and it will now from this prediction tell us what the estimated pitching moment would be at that point. Okay, one last thing I just want to point out is that mockup 4, and let me just pull that up real quick. Mockup 4, when you're looking at airfoil information, it's asking for these parameters. So these are the parameters that we just solved for. So the 0 lift angle of attack, and notice it wants that in radians. The lift slope in radians again, or per radian. And then it actually kind of mixes these two definitions for pitching moment. So it asks for the 0 lift pitching moment, which if we come back over here, it's actually this value here. This is the pitching moment at 0 lift. And then it's going to ask for the lift, or the slope of the pitching moment as a function of angle of attack. Okay, so it actually asks for these two values here. So those would go in here. There's our 0 lift pitching moment, our moment slope per radian, and then here's our 3 drag terms. It calls this the 0 lift CD. And so if we come back over here to our drag, these are the 3 drag terms that we solve for. This is the 0 lift CD, and the reason you know that is because if we plug in 0 for our lift coefficient, these two parameters don't matter. Remember, because it's this one gets multiplied by the lift coefficient, this one gets multiplied by the lift coefficient squared, and so if our lift coefficient is 0, then all that's left is this. So this is the drag at 0 lift coefficient. Actually, it's the location where this drag plot crosses the y-axis. Remember, because we plotted this as a function of lift coefficient, so it's the point where that crosses the axis there is the point 0061. So that's what it's asking there. So that's our 0 lift drag coefficient, and then this is the drag component that's going to get multiplied by lift, and then this is the drag component that's going to get multiplied by lift squared, or CL squared. Okay, so these are those other two terms. This is the linear term and the quadratic term of that equation. And then mockup also allows you to put in a maximum lift coefficient if you want to estimate the stall angle of attack, for example, of the entire aircraft or the wing, based off of the stall lift coefficient of the airfoil. So you can put in a max lift coefficient there. Okay, so this is how This basically characterizes that airfoil, or the airfoil that's being used inside of this wing. And by the way, in mockup you can actually choose two different airfoils if you want, one at the root and one at the tip. The default is to say that they're the same, but if you uncheck this box, you can put in a different airfoil information for the tip, and then it will actually linearly interpolate from the root to the tip. It will linearly interpolate those properties out to the tip. So, okay, so I just want to give you an overview of how to come up with those coefficients, from traditional data. So usually this is the data that you'll have up here that we started from. You'll have angle of attack. Usually that's reported in degrees. You'll have a lift coefficient, pitching moment, and a drag coefficient. And I just wanted to show you how you whittle that information down to just a few parameters here that then can be used to characterize the aerodynamics of that airfoil as a function of angle of attack. And that's what's often used in these other software packages that then are trying to predict the aerodynamics of the entire aircraft, because that's built on the aerodynamics of an airfoil.